Today I will discuss general product spaces. So far we have discussed product of two topological spaces. By general product space, we mean product of any arbitrary collection of topological spaces. Before coming to general product space, we need to define Cartesian product of any arbitrary collection of sets. Let x lambda, lambda belongs to capital lambda, be an arbitrary collection of sets where capital lambda is the index set. Then the Cartesian product of this collection is the set of all mappings x from capital lambda to union of x lambdas such that x lambda belongs to capital X lambda for each lambda belongs to capital lambda and is denoted by product of x lambda, lambda belongs to capital lambda, or Cartesian product of x lambda, lambda belongs to capital lambda. The set x lambda is called the lambda-th coordinate set of the product. So, by Cartesian product of this collection of sets, we mean the set of mappings from the index set to union of all these sets. And x lambda is called the lambda-th coordinate set of the product. We denote the mapping, the image x lambda by x lambda, and so this Cartesian product can be written as the set of all mappings x from the index set capital lambda to union of x lambda such that x lambda belongs to capital X lambda for each lambda in capital lambda. For our convenience, we denote the mapping x by x lambda. Lambda belongs to capital lambda and x lambda is called the lambda-th coordinate of x. Here we are using the similar notation as in sequences because in a sequence the domain is the set of natural numbers, so we denote the sequence by its images as xn belongs to capital N. Now we define projection. Let x lambda, lambda belongs to capital lambda, be an arbitrary collection of sets and let x denote their product, Cartesian product. Then a mapping pi lambda from the product of these sets to x lambda defined by pi lambda of x is equal to x lambda for each x belongs to capital X is called the lambda-th projection of x. Here pi lambda maps to each element of x to its lambda-th coordinate of x. Now we define product spaces. Let x lambda, t lambda, lambda belongs to capital lambda be an arbitrary collection of topological spaces and let x denote the Cartesian product. Then the topology T on the Cartesian product x which has the subbase, the collection B star consisting of pi lambda inverse G lambda. Lambda belongs to capital lambda, G lambda belongs to T lambda. So actually we are taking inverse image of open sets in x lambdas and that collection is B star and this collection is the subbase for the topology T which is called the product topology or the Tikhonov topology on X, and X with this topology T is called the product space of the given topological spaces. The collection B star is called the defining base for T as this is the subbase for the topology T. So by taking finite intersections of its members we get the base for T and by taking their unions we would have all the members of T. We note that for any open set G lambda of X lambda, pi lambda inverse G lambda, which is any member of the subbase, this is the set of all X in the Cartesian product whose lambda coordinates are members of G lambda, and coordinates other than lambda coordinate are unrestricted, means any member of X lambdas. So pi lambda inverse G lambda is the set of all mappings or all the elements of the Cartesian product for which X lambda belongs to G lambda. Alternatively, we may write pi lambda inverse of G lambda is the Cartesian product of Y alpha, alpha belongs to capital lambda, where Y alpha is equal to G lambda for alpha is equal to lambda. That is, in this Cartesian product, lambda coordinate is equal to G lambda and other coordinate sets are as in the product space. That is, Y alpha is equal to alpha X alpha if alpha is not equal to lambda. So we can find any element of the subbase for the topology, product topology T on X. Now we shall prove a theorem which gives a characterization of the product topology. Let X lambda, T lambda, lambda belongs to capital lambda be an arbitrary collection of topological spaces, and let X is their Cartesian product. Let T be a product topology let T be a topology on X, then the following statements are equivalent. Statement A is T is the product topology on X. Statement B is T is the smallest topology for which the projections are continuous. Let us prove this theorem. First, we shall prove that statement A implies statement B. So, let T be the product topology on X. And we know that for any um, T lambda open set G lambda, pi lambda inverse G lambda is T open because this is a member of the subbase and so this belongs to the topology and so this is T open. And so projection pi lambda is T lambda continuous for each lambda belongs to capital lambda because inverse image of any T lambda open set is T open and so projection is continuous. So we have shown that if T is the product topology then projections are continuous. So it remains to show that T is the smallest topology. So consider any other topology. Suppose we be a topology on X such that pi lambda is continuous for each lambda belongs to capital lambda. Then for each T lambda open set G lambda, pi lambda inverse G lambda is V open because pi lambda is continuous. So inverse image of any open set is open, it must be open in the topology. So pi lambda inverse G lambda is V open. As V is the topology, V contains all the unions of finite intersections of the following collection. Because we have seen here pi lambda inverse G lambda is open, and so if we take union finite intersections of these members, then that will be in the topology, and if we take their unions also then we get the members of V. So V contains all the members because V is a topology, and so since this is the subbase for the product topology, and so we can say that V contains all the members of T, where, whereby T is coarser than V. V is any topology on X for which projections are continuous, then we have shown that T is coarser than V. So T is the smallest topology on X for which projections are continuous. Now we show that B implies A. So let T be the smallest topology for which the projections are continuous. We have to show that T is the product topology on X. Since projections are continuous for T, therefore pi lambda inverse G lambda is T open for G lambda belongs to T lambda for each lambda in capital lambda. Let B star is the collection of sets of this form, pi lambda inverse G lambda. Lambda belongs to capital lambda, G lambda belongs to T lambda. So, for any topology V on X, projections are continuous if and only if this collection B star is contained in V, because for any topology, if projections are continuous, then that topology must contain these sets. And so, if V is any topology for which projections are continuous, then that topology must contain B star. But here we are saying that T is the smallest topology for which projections are continuous. So our T must be generated by B star. That is, the topology T has the subbase B star. And so we can say that T is the product topology on X. Thank you.